The air in Lab 6 thrummed with a palpable sensation. Cool, sterile air circulated, carrying the faint scent of ozone and the metallic tang of immense power. Banks of servers lined the walls, their lights blinking in complex, silent conversations. Scientists, cloaked in pristine white, moved with quiet intensity, their faces illuminated by glowing monitors. Each screen displayed torrents of data, the language of a new world. Years of dedication converged here, focused on a single, audacious goal to birth a new kind of mind. The silence was profound, filled with an unspoken tension, like the moments before a storm breaks. Every hum of the cooling systems, every soft click of a keyboard seemed amplified. This was more than a laboratory. It was a crucible forging the future. Today was different. A subtle shift in the energy, a new level of focus. The final calibrations were complete. Diagnostics had run their course, and all systems reported nominal. Green lights cascaded across control panels, a silent digital affirmation. The team gathered, drawn together by an invisible current, their eyes fixed on the central chamber, where Helios waited, ready to awaken. The dawn of a new computational era felt imminent. Classical computers think in a straightforward way, using bits, simple switches that can be on or off, 1 or 0. This binary language underpins everything, from smartphones to global financial networks. It is a system of definite states, clear answers, yes or no, true or false. Powerful, but with limits. Some problems are too complex, too vast. Quantum computing is radically different, operating on principles that defy everyday intuition. It uses qubits, not just bits. A qubit can be 0, 1, or both simultaneously. This is superposition, a state of pure potential. Imagine a coin spinning in the air, neither heads nor tails until it lands. Then there is entanglement. Two qubits can become linked, intimately connected, regardless of distance. Measure one, and you instantly know the state of the other, as if they communicate faster than light. This interconnectedness allows quantum computers to explore vast numbers of possibilities at once. A classical computer checks paths one by one. A quantum computer explores all paths simultaneously. This difference is not merely quantitative, it is qualitative, a fundamental shift in how information is processed. Quantum computing offers a key to unlock previously intractable challenges, promising a revolution. Helios was not just another quantum computer, it was a statement, a monument to human ingenuity. Its core lay suspended, deep within layers of cryogenic shielding, cooled to temperatures colder than deep space. This extreme cold was essential to protect the delicate quantum states of its qubits. Inside this frigid heart, 512 qubits resided, each a precisely engineered superconducting circuit. Their coherence times were record-breaking, allowing for more complex calculations. Helios featured a novel coupling architecture, enabling intricate entanglement patterns. The name Helios was chosen carefully, after the Titan god of the sun, a bringer of light. The team believed their creation would shine a light on problems previously hidden in computational darkness. Its construction had been a decade-long odyssey, pushing the boundaries of materials science and engineering. Helios represented a new threshold, designed for discovery, to simulate complex quantum systems and probe the very fabric of reality. Its activation marked a pivotal moment, the dawn of practical quantum advantage. Behind the gleaming metal and cryogenic chill of Helios lay a very human story of relentless perseverance. Dr. Eris Thorne, the project lead, was a visionary, his conviction the project's unwavering North Star. The team was a mosaic of talents, young postdocs, seasoned engineers, theoretical physicists, and software developers. They shared cramped offices, consumed endless cups of coffee, and debated passionately over lines of code. There were frustrations, moments of despair, experiments that failed spectacularly. Alara Vance, chief quantum engineer, recalled the early days. "We were chasing ghosts." The pressure was immense, yet a shared purpose bound them. The belief they were building something transformative. They weren't just assembling hardware or writing software. They were explorers charting unknown territory. Each successful qubit stabilization, each validated algorithm was a small victory. They poured their intellect, energy, and hopes into the cold heart of Helios. It was more than a machine. It was a reflection of their collective aspiration. The experiment was designated Kronos 7. Its objective to simulate the quantum evolution of a complex, closed system. The team expected to see the entropy increase as quantum information diffused through the system. The simulation began. Helios hummed its silent, cryogenic song, and data streamed onto the monitors. At first, everything proceeded as predicted, but then the unexpected, the anomaly. The entropy curve, which should have continued its rise, suddenly flattened, then dipped. The control room fell silent, eyes darting from screen to screen. Was it a sensor glitch? A calibration error? A subtle flaw in the algorithm? They ran diagnostics, checked every parameter, recalibrated, and ran Kronos 7 again. The anomaly reappeared, identical, precise, unmistakable. It was not an error. It was real. The system, for a fleeting moment, seemed to defy the expected flow of information. A whisper from the quantum void, a pattern that should not exist. Helios had not just performed a calculation, it had shown them something new, something profound. The Kronos 7 anomaly sent shockwaves through the lab and the wider physics community. Initial skepticism gave way to intense scrutiny. The implications were staggering. If information in a closed quantum system could momentarily reverse its entropic spread, what did that mean? Did it challenge fundamental tenets of thermodynamics or hint at deeper, undiscovered principles? The data was irrefutable. Helios had observed it, forcing a re-evaluation of long-held assumptions. Some theorists posited that the anomaly might be evidence of a subtle, universe-scale feedback mechanism. Others wondered if it pointed towards a connection between quantum mechanics and the geometry of space-time. The dip in entropy was tiny, fleeting, but its existence was a crack in our understanding of reality. Helios had not just solved a problem, it had posed 1,000 new questions. The power of Helios and the quantum computers that will follow is immense. It promises breakthroughs in medicine, material science, artificial intelligence, and climate modeling. This potential is exhilarating, a beacon of hope, a testament to our species' relentless drive to understand. However, with great power comes profound responsibility. The same quantum capabilities that can design life-saving drugs could also be used to break encryption standards. The Kronos 7 anomaly serves as a warning. We are probing the fundamental nature of reality. The path forward requires more than just scientific brilliance. It demands wisdom, foresight, and a deep ethical commitment. The development of quantum technology cannot occur in a vacuum. It must involve a broad coalition. Open dialogue is crucial. We need to anticipate potential misuses and establish safeguards. As we stand on the cusp of this new quantum era, we must proceed with both ambition and caution. Helios has opened a door to a universe of possibilities and perhaps a deeper understanding of our place within it. Let us explore this new frontier with courage, humility, and an unwavering commitment to using this extraordinary knowledge for the good of all.